Hello again, welcome back to ptet.chemistry channel. So this is Mr. On, and this is the fourth of 10 video series on these infographics, which are not syllabus specification, which are not a content tutorial. So you can skip this video if you are not into this kind of thing. This is about topic connections, and these were provided by Cambridge Assessment International Education for free during the pandemic. I managed to get a hold of it, and a copy of this file is available as a Google Drive download link in the video description below if you just scroll down to the video description. Alright, so as I mentioned, these are not syllabus specification or neither are these content tutorials, and what I'm merely showing you really is how in this organic chemistry part 1, how the topics are related together, which sometimes learners find it hard to relate because why are they learning this? Why am I doing this? Why am I doing that? So you can see the interconnection between the different areas of organic chemistry, which I'm sure you have realized. And a lot of students struggle with organic chemistry as a result of the huge complexity of it and how they are more interrelated to each other and to other branches of chemistry, other than just independently being, discrete information on its own. All right. So as chemistry students, we have realized that they have done formula, functional group, as well as naming. So talking about the number of carbon, so these are the international standards of MEF, EF, prop, put, pen, and hex, and of course it goes on and on. And then identifying functional groups are very important as well in organic chemistry. That's the first thing that students should be doing when they are given an organic compound. Identify functional group and think about what sort of reactions are associated with that functional group. Yeah. Okay, so naming of organic compounds are becoming a normal thing that examiners like to ask as well, whether they give you the name of the compound and you're asked to draw it or to interpret it or to use it, or they might be showing you a structure and they ask you to name it. Okay, the first bit of hydrocarbons comes under, they come in the form of alkanes. So in O-level GCSE, you have done that alkane can undergo combustion. So there's combustion in excess oxygen to give you CO2 and H2O. They could undergo substitution, but not addition, because of the carbon are saturated already. So it's just substitution reactions, and they give you halogenalkane, which is actually another functional group that you cover in AS chemistry. Okay, and you can do cracking. So this is about a simple cracking you can do in the lab. You collect the gas over water, because the gas that you're expecting is either a mixture of hydrogen or it could be a hydrocarbon, both of which are insoluble in water. That's why collection over water is a suitable method for collecting the gas from cracking. Yeah, so this is just thermal cracking. You should have added a bit of catalyst in there, like Al2O3 or SiO2. Otherwise, it's going to take a lot more heat in order to undergo the cracking and produce you the desired shortened chain or branch alkane or alkene or hydrogen gas. Yeah. If I go straight to this on the right hand side here, you get characteristic organic reaction, as I mentioned. Are they addition? So what is meant by addition? When two things add together, you just get one product. Substitution, when two things add together, you still get two products, but one group has substituted or replaced the other one. Okay. Elimination is the opposite of addition, where one substance breaks apart, eliminate or kick out one thing, and therefore you get two things out of one thing. You get more than what you put in as elimination. Yeah. So condensation and hydrolysis are actually kind of opposite of each other. But you have done condensation polymerization in on O-level GCSE. You have known that condensation polymerization is when the monomers add together and they kick out a small molecule, right? So condensation is, instead of polymerization, it's just a small scale reaction where two things react and they kick out a small molecule, could be H2O. In A2 chemistry, you have learned that it could be HCl or etc. Yeah. So it kick out essentially a small molecule as a result of the two things adding up together. All right. So the small molecule that kick out it's not necessarily the whole of A or the whole of B, but it's just a part of them that gets condensed together and kick out this small bit. Yeah. So you know that it's not just esterification, but also when you form amide as well. So there's actually a condensation reaction as well, forming an amide. Oops, I was about to draw an ester there. So both of which something you have done in GCSE or O-level, and you revisit it in AS chemistry. Hydrolysis is basically just breaking apart the the bond in one particular kind of functional group, such as an ester. You see, you can break this bond. If I use a different color, you can break this ester bond, you can break this amide bond. That will give you the carboxylic acid component, that will give you the alcohol component, and here this will give you the acid component, and this will give you the amine component. So a lot of students didn't realize that the acid component there are acidic. So when you do base hydrolysis, you will never get the acid itself, you will get the salt of the acid if you do base hydrolysis. Obviously, if you're in acidic hydrolysis environment, you could get the carboxylic acid instead of the salt. Yeah. Hydrolysis is not just using H2O. Sometimes you could use NaOH as well. That's why when you have halogenalkane, we talk about hydrolysis of halogenalkane because you're using the NaOH in the presence of water, right, to do the hydrolysis. But there is a substitution, which is also known as hydrolysis of halogenalkane. So next to the alkane functional group, you have these alkenes. The carbon-carbon double bond versus the carbon-carbon single bond is a very important branch of compare and contrast in organic chemistry. So I've put out a couple of videos that specifically target questions that ask on carbon-carbon single versus carbon-carbon double bond kind of chemistry. So you can watch on that topical playlist. They come under, I think, 10.2 as part of hydrocarbons, where the alkane and alkene chemistry have been grouped together. Yeah. So next bit is actually this isomerism, structural and stereoisomerism. So even though they put it 14.4, staying in my topical playlist, I put it under introductory organic chemistry. So together with all the naming and naming and isomerism and stuff, there's a lot of things they can ask you. So whether they ask you to draw the mirror image, where you need to show about the 109 degree separation between the two groups, and of course the one that the two kind of wedges, the one that's bolded is coming out from the screen, is pointing towards you right in the eye, whereas this wedge one is pointing away from you into the screen or into the paper itself. Okay, so it's very important that you draw something that depict or that illustrate the three-dimensional representation. When you do the mirror image, make sure you always try to draw a dotted line for the mirror image, so that you're just reflecting whatever groups or substituents onto the other compound as part of the mirror images. Yeah, and then the cis and the trans isomerism. So there's a naming to it. We always look at the group or the substituent atom. They are of bigger mass. Between chlorine and hydrogen, chlorine is heavier. Between chlorine and hydrogen, chlorine is heavier. So the heavy and the heavy one, okay, they are opposite each other. They are not on the same side of the carbon-carbon bond. So this is the trans, which is the E, and this is the cis, because this between hydrogen and chlorine, this is the high priority group. Same deal here. This is the high priority group. They are on the same side of the carbon-carbon double bond. You can get the cis isomerism. But between the cis and the trans, they are not the same, because you cannot rotate about the single bond, whereas you could rotate freely about carbon-carbon single bond. Okay. Structural isomerism is something that a lot of students struggle with. What I advise you is practice your skeletal formula and draw all the possible structural isomer for n equal to 1 up to n equal to, 5 or 6. Not just for alkane, try it for alkene, try it for alcohol, try it for halogenalkane, try it for aldehyde, ketone, carboxylic acid, and also esters. Because by doing that, you will have realized that in A-level chemistry, aldehyde and ketones are grouped together, because if you have the same number of carbon, aldehyde and ketones are actually structural isomers. Okay, so you could practice your structural isomers while also practicing your skeletal formula. From the skeletal formula itself, you should be able to write out structural formula and of course draw the display if you have to. But really, you do not want to be drawing display throughout your A-level chemistry. Okay, that is really slow. Okay, unless the question specifically asks you to draw display formula. Whereas carboxylic acid and esters, if the total number of carbon are the same, carboxylic acid and ester are another combination that will give you structural isomers, specifically functional group isomer, just like aldehyde and ketones. Yeah. Moving on to this, I'll talk about infrared spectroscopy last because it's an analytical technique. But moving on to halogenalkanes, the most common kind of chemistry asked around halogenalkane revolve around SN1 and SN2 mechanism. You will find that from my topical playlist, I think I've got a couple of videos on SN1 versus SN2 type reactions, because they are the most common type of chemistry that are associated and being asked about for halogenalkane chemistry. Both mechanism of which involve the breaking of the carbon-halogen bond. So that relates back to bond energy, where they can ask you some bond energy calculation question, where they can ask you to relate to the bond energy and also the bond polarity as related to the reactivity. Which one is more important? And based on your observations, you know. So based on your observation, like if you add in a silver nitrate solution, how fast will the precipitate form, etc., etc. This can all constitute part of experimental planning or experimental design kind of question, which indeed has come a couple of times. Yeah, so you can watch some of my experimental planning videos under paper 5 if you are interested. Okay. As I mentioned, the relative strength of the carbon-halogen bond can be manipulated in terms of what they form, such as this tetrafluoroethene. Tetrafluoro, because there are 4 fluorine on the ethene. So when you form the addition polymer, you get this straight chain, which are all carbon-carbon single bond, because you know that you've done the addition polymerization. So in this addition polymer, it is called Teflon, and it's the non-stick cooking pan, and you know it's safe for cooking because of the strong carbon fluorine bonds. They are not easily broken, they are not easily decomposed at all, even under extreme heat. Yeah. Other things include, well, like I said, Teflon is used in making the non-stick cooking pan. Other things include the use in aerosols. Okay, you use it in aerosols. And also, but obviously this can damage, this can cause damage or harmful consequences to the environment, such as the destruction of ozone layer as a result of, let's say, radicals such as chlorine radicals or bromine radicals or even iodine radicals. Which one will be formed more readily? It all comes down to the bond strength. The weaker the bond, the easier it is to break them. And you have done something called homolytic fission. That is how you get the radical reaction going on in the first place, and those things can react with the ozone and further destroy it. Okay, when they react with ozone, you no longer have ozone, you release them. Yeah, okay, you form something else. So this is quite a video, so this is quite a long video and it's on so far. Anyway, I'll try and speed it out a little bit. So now you have alcohols. Alcohols are this compound. They contain a hydroxyl here, connected to alkyl groups. As I mentioned, you should know how to draw a skeletal formula and try to think about all the isomers of primary or secondary or tertiary alcohol associated with, I don't know, 2 carbon, 3 carbon, 4 carbon, 5 carbon, even up to 6 carbon. Anything more than 6 would have been very tricky for A-level standard and very tedious as well. Yeah? So alcohols can undergo combustion. They can undergo oxidation to give you aldehyde or to give you carboxylic acid. You should know that you can stop here if you want to. So you need to know you just heat and distill immediately, or you oxidize all the way under reflux conditions with an oxidizing agent. Yeah. Of course, you can dehydrate the alcohol. You meaning to say you eliminate the OH and a H from the carbon next to it to give you the alkene. And you could also form these things, which is O minus and Na plus, and it will give you half H2 when you have ROH plus sodium. So this is essentially a redox reaction. If you are being asked what kind of reaction it is a reduction and oxidation reaction. The sodium go from sodium 0 to become sodium plus 1. The hydrogen go from hydrogen plus 1 to become hydrogen 0. The most complicated thing associated with it is people always thought that, you know, one of these give you 1 mole of H2, when in reality, when you balance the equation, you can see one of the OH group give you only half of a H2 molecule. This can be associated with a mole calculation kind of question. Yeah, of course, they can ask you tests for the hydrogen gas as well. Next bit is on this aldehyde and ketones, very big part of AS level organic chemistry. So I don't like what they have done here. They have just written down Cr2O72-. That is not technically correct. You need the acid. Without the acid, the redox will not work. So this is orange in color. It will turn to green. That is when it will form Cr3 plus aqueous. So this is orange and this is green. only if you could oxidize something such as a primary alcohol, a secondary alcohol, but not a tertiary alcohol where it will remain orange. Okay, if you want to start with aldehyde, as I mentioned, you just need to heat and distill immediately because this has lower boiling point than the alcohol. So if you distill, this one would come out first because it has the lower boiling point, since it cannot form hydrogen bond between the molecules, but this one can form hydrogen bond between the alcohol molecules. Secondary alcohol, so primary alcohol, secondary alcohol, they are different. You look at the carbon with the OH, how many other carbon is it bonded to? Okay, so in this carbon with the OH is bonded to one other carbon, it's a primary alcohol. This carbon with the OH is bonded to two other carbon, it's a secondary alcohol, etc., etc. Okay, so test for ketones and aldehydes. So usually it's the aldehydes that will be positive with a Tollens reagent and also Phalanx reagent, because you can oxidize aldehyde further, but you cannot oxidize ketone further. You can watch some of my tutorial playlist questions on carbonyl compounds, aldehyde and ketones, to see what kind of other questions could be asked. Yeah. In a carboxylic acid chemistry, we talk about the formation of it from oxidizing primary alcohol, or from oxidizing an aldehyde, or from a hydrolysis. So this is not oxidation, this is hydrolysis of something called nitrile, whereas this one is oxidation, this one is oxidation. And from the carboxylic acid itself, you can get the salt, which is with sodium, you can get this, or with sodium hydroxide, you can also get it, all right? So this is a salt. You can either use metal, so metal plus acid will give you salt and hydrogen gas, or you can use a base, because this is acidic. A base plus acid will give you salt and water, not hydrogen gas. All right, you could reduce it back all the way to primary alcohol, but you need a very strong reducing agent such as lithium aluminum hydride, but sodium borohydride will not reduce carboxylic acid, as well as if you use hydrogen and palladium, that will also not reduce a carboxylic acid. All right. What else? We talk about the formation of esters from carboxylic acid and alcohols via a reaction called condensation. So you know this is the ester bond that you can hydrolyze. That will give you the acid bit, that will give you the alcohol bit. When you name ester, you name the alcohol bit first. So this will be like alcohol, whereas this is the carboxylic acid, but the name will be alkyl carboxylate. So you name the alcohol bit first as an alkyl, and then you name the carboxylic acid bit as the salt bit, okay, which is the ATE, okay. And of course you can hydrolyze it under acid to give you back the acid and the alcohol, or you hydrolyze it under base where you get the carboxylate salt because it's acidic in the basic condition, and you could get back the alcohol. So these things are interrelated to each other, and it's just a quick overview of your AS topic, and by no means these are your specification of your syllabus. You should check on what you need to cover totally. Yeah. So thank you for watching. I'll see you in the next video, and you can grab a copy of this file from the Google Drive link in the video description. All right.